Hey, and welcome back to this Smart Account from Scratch series. We are on step 3, account validation. This is my favorite part of this series because this is where it starts to feel a little bit more legitimate. We're going to make it so not any person can sign user operations that execute against this smart account, only the owner. Right? That's really important. Now it's starting to feel like a real smart account because only the person who owns a smart account can sign user operations against a smart account. Now, something that you'll notice about this, which is the beauty of account abstraction, is we're rolling our own validation logic, right? If we wanted to have multiple owners, if we wanted to use a different type of cryptography here to do the verification on chain, we could do that. It's up to us. For us in this particular case, I'm keeping it simple. We have one owner and we're going to use elliptic curve digital signature algorithm from OpenZeppelin. But like I said, you could do whatever you want here, right? This is your account, and that's the beauty of account abstraction. Let's go ahead and jump into this. So I have the repository that we have here from the previous step. I have a hard hat node that was just started, and to prove that to you, I'll just restart it, right? So that we know there's no previous state on the node. And what we're going to do is we're going to go ahead and install that OpenZeppelin library. We actually already have it installed in our node module, so I'm just going to go ahead and pull it in. I'm going to import it. OpenZeppelin, I want to get the ECDSA cryptography utils here. And in the ECDSA cryptography utils, what I'm going to do is I'm going to pull out two methods. Let's go look at them to try to find those methods. One is going to be called recover. So here's the recover method. It's going to take a hash and then a signature. And what it's going to do is it's going to recover from that hash and signature the address who signed that particular hash. So this is going to be, someone's going to, on the front end, or in our script in this case, is going to be signing a message, and on the back end in the smart contract here, we're going to be recovering who that address was that signed that message. Only they could have possibly signed that message. Something that's kind of important to note here about elliptic curve digital signature algorithm when recovering addresses is that it's important that you hash the message or hash whatever it is that you are signing. OpenZeppelin actually makes a note here that it is possible to craft signatures to recover arbitrary addresses for non-hash data. So you are going to see me hashing the message and the user operation when we get to that point. And this is why. So we are going to use a hash here, recover the address from the signature. So recover is one method that we're going to use. The other method that we're going to use is like ETH sign message hash. There we go. I'm going to copy this because I always forget the name of this method. What it's going to do is it's going to take a hash that we give it. So we already got to get a hash. It's going to be a catch-ack hash. And we're going to provide it to this function. And then it's going to do this EIP191 sign. This is a standard for doing Ethereum message signing. One of the big reasons why this is a standard is because you don't want to have it where transactions that are actually valid on the Ethereum chain could also have the same, they could also be used for this, right? You want to sort of differentiate the messages that are being used on chain versus transactions that are running against the chain here. So there was a standard created for this that's called EIP191. You could definitely look it up and see more of the details there. We're going to be using this here for our signature verification. So there is our to ETH sign message. We'll be doing this on both the front end with the script, and we'll be doing it on the back end with our smart contracts here. So let's go ahead and pull that in. Now, I always get this wrong because it's very difficult to do this stuff, this cryptography, especially with the front end tools and the Solidity tools. It's very easy to forget to hash something or put things in the wrong format, especially when you're working with JavaScript, where maybe you didn't turn something into a byte array when it should have been a byte array. Instead, it's just a hex encoded string, something like that. So what I'm going to do first is just sort of test this out. So I'm going to create just like a test contract, and all this test contract is going to do is help us see whether or not we can make this work properly. So it's going to take right now a signature, and let's just call that sig. And what I'm going to do is I'm going to use this to ETH sign message hash and also the recovery method to see if we can recover the same address on chain that we signed with off chain. And if we can get there, then we can move along really fast from this point. So what I'm going to also do is, because I'm using hard hat, I'm going to do console.sol. And here I'm going to be able to log out what the recovery address that we get is. So let's go ahead and do this. We're going to do exda.toEthSign message hash. For this particular example right now, what I'm just going to do, keep things really simple. I'm just going to sign a message like we here and just put it inside here so that we can sign something off chain, sign something on chain that is going to recover the same address. And then we could talk about what we really should be signing after that. So let's go ahead and do this. We're going to do recover. Remember, recover takes a hash and then it takes a signature. So this is going to return an address, which is the recovered address. And then we're going to console.log that. And if it's the same address as the one that actually signed the message off chain, then we know we've accomplished this step properly. So let's go ahead and just put in here, this is going to be, can we take that from call data or memory here? There we go. Because it's constructed, we got to take it in from memory. So then we pass that signature in there and recover it. Awesome. Okay, so now on our front end, to keep things really, really simple, I'm just going to create another script. It's going to be called sig. I'll take this test script here. And what I'm going to do with the signature is I'm just going to deploy the test contract that we have here. And I'm going to pass in a signature and just test that we can recover the address that actually signed it on the smart contract side. So let's go ahead and do that. I have this get contract at, but I really want a get contract factory for test. And we're going to deploy that test. I don't need any of these addresses. This is going to be a capital test. And then we're going to deploy the test by saying await test.deploy. And I don't need to do anything else because we're console logging the address that's happening here. So what I do need to do though is pass in a signature right here. And this is what we're actually going to be testing. Okay, so to get this signature, what I need to do on the front end or in my script here is I need to make a signature of that message we. So Ethers has a couple tools to make this easy. Depending on what you're using, should have cryptography tools to also sign messages. One of the things that we can do is with Ethers, we can grab a signer. So I'm going to grab the first signer in the list of all of our signers. These are the signers that are here in the local blockchain node when we are running it against this local blockchain node. So I'm just going to grab that first signer. I'm going to say hre.ethers.getSigners. And the first one that comes out of that array is going to be my signer 0. And then with signer 0, what I'm going to do, let's leave that there. With signer 0, what I'm going to do is I'm going to sign a message. So let's call this my signature. I'm going to say signer 0.sign message. And now the message is the top part, right? So we got to get that we. Right? We have that string we, but this has got to be the hash of the string we. And really, in order to get that to work properly, you need to take this string and turn it into UTF-8 bytes. Ethers has a utility for this called ID. So if I use hre.ethers.id here, I can pass in that string. And if we look at this ID method, you can see it's turning into UTF-8 bytes and it's taking the catch hash of that. So very handy that it has it here. If the library that you're using doesn't have that, you may have to do both of these things to UTF-8 bytes and then cache it. The other thing that we do need to do here, which is a little annoying and threw me off when I was first trying this, is we do need to turn this into a uint8 array. And a uint8 array is going to be bunch of bytes here. So what we need to do is we need to say hre.ethers.getBytes. This is a method on Ethers version 6 that is going to take this hex encoded string and turn it into a uint8 array so we can actually sign this message. This is what I was talking about where it gets confusing, right, with the different types, especially when you're using JavaScript, to make sure that you are getting the type that you need and that the cryptography works out on both ends. Not even entirely confident that this is exactly right, but that's why I set up this test apparatus to make sure that we should be getting the same address on the smart contract side as we get on the front end, and then we can move forward from there once we know that that's all set up properly. Okay, great. So we have the signature here. I'm going to go ahead and pass that through. And the one thing that we do want to test, this is the address that we're getting on the front end. is await signer 0.get address here. This is the address that we have on the front end. And then on the back end in the smart contract, it'll also log out an address, right? So if that address is the same over here, the recovered address, that's also using this hash of the message then we know that we've done everything properly here. So we can move on from that point. So let me go ahead and run this and see if it's working. The other thing that I'm going to do here that's just going to make it a little bit easier is I'm going to run this script against a local temporary hard hat node. So not the one that's running on localhost A545, but one that's actually just going to run ephemerally inside of this process. So I'm going to say npx hard hat run scripts / sig.js network is going to be hard hat. So this is going to be a temporary blockchain that's just spun up for this process of running this sig.js here. And that's going to show me the console.log, which is what I want to see. So let's see if this works. Okay, great. So that actually looks like the same address. So, yeah, I'm a little impressed, actually. I didn't think that was going to work the first time. Usually I get these things wrong, especially with some of this stuff on the front end. Fortunately, this is all working properly here. So we can actually move on from this point. We can move this logic now into the account. So that's really great. Let's go ahead and do that. So what I'm going to do now is I'm going to move this x the recover method into the account itself. And we're going to use that to validate that the owner was the person who signed this message, right? So let's go ahead and do that. I'm going to get rid of the test contract. I'm going to leave the SIG file over here for now, but we'll eventually get rid of this. We don't need this. This was just for testing, but I am going to use this because I always get this wrong, and I want to make sure that we reuse that for our execution of the user operation. So what I'm going to do is I'm going to take in the stuff over here. Recovered is going to be x the recover of a message. The signature now we actually get from the user op, because if you remember in our execute function, right, we have our execute function, we have this signature that actually gets put in here inside of the user operation. That's actually going to be used to validate this on the smart contract account, as we're seeing here, right? So right now the signature is 0x. That's what we're going to change in this stage. We're going to go ahead and make the signature something that can be validated on chain. So this signature is going to come in here as part of the user op, which is the first argument passed to the validate user op function, as you might expect, right? So we say user op here and we say signature, and there it is. That's the signature that's passed through. And now we're actually validating that somebody signed this message and that person, this recovered, should be the owner. So we're going to return owner is equal to the recovered address. Now, validate user op doesn't return a Boolean necessarily, right? It returns this validation data, which right now we're using kind of like a cheat code, which is that we know that if validation data returns 1, that's an invalid signature. 0 is a valid signature. I'm keeping it that simple for now. So what I'm going to do is I'm going to say that if owner is equal to recovered, if we got the same person who signed that message is the same as the owner of this account that we passed in the init data in the constructor here, then we can go ahead and say that this is a valid signature, otherwise not a valid signature here. And what do we get in here? It says, okay, so now we're actually reading from state, so we need to change this from pure to a view. Okay, great. So we got this validate user op. This should be working pretty well. So let's just go ahead and do that. I can get rid of my console.sol now. And let's go ahead and bring this logic over into our execute. So in our execute now, we need to change the signature, right? So let's go ahead and make the signature. It's going to be this signer0.sign message. Signer0 is also the name of my signer0 up here, right? I use the same one. So I'm going to go ahead and do signer0.sign message, take all this stuff out and put that in here. And that should be all we need to do to pass that signature along. And now we should be able to execute a user operation where only signer 0 could sign that message and we can recover it on chain. So let's go ahead and do some of this other stuff here where we have Because we're starting from scratch again, we need to, again, send in the init data so we can recreate that smart account, and we can deposit against the paymaster, and then we can go ahead and execute this user operation. So let's first, again, deploy our contracts that we need to deploy. Maybe these addresses will be the same. Let's see, factory address, entry point address, and yep, they look the same. That's great. Again, because we're starting from that same mnemonic every time, so that's really helpful. So I can leave those in there. And then now we're init coding. We can actually go ahead and run this, execute, and I think everything should work fine. We're doing the signature over here in the script, and then we're validating that inside of the account. So let's see if we're able to get this to work. No, it says init code. Sorry, I got a little something in front of me here that I can't see that. Init code failed or out of gas. OOG stands for out of gas here. So what I think happened in this case is maybe my gas values are a little low. I'm going to have to adjust them in the guide, so hopefully you won't run into this issue. So I'll go ahead and double those just to give us a little bit more buffer room there. I'm pretty sure that's the issue here because I don't think the init code has changed at all. So we must be running out of gas. Again, these error codes are really helpful. You can go look them up inside of the entry point. I'm not going to do that in this case because I think we're just running out of gas. So let's go ahead and run that execute again, see if it's okay. Cool. So we're just running out of gas. I'm going to adjust those in the guide so that hopefully you don't run into that issue. But yeah, there we go. So it looks like the execution worked. Now we have the sender address. We can go test it to make sure that the count was incremented. Let's go make sure. So we have this. I don't want to do any of this other stuff anymore. Pretty confident that our paymaster is working properly. So I'm just going to go ahead and run test. There we go. We have an account. And now we can do everything else that we were doing before, which is that we could, comment this out. Boop. Not send money to the paymaster address again. Execute it again. Maybe one more time. And we should be on count 3, right? Oop, I did. Yep, there we go. So we're on count 3. Okay, great. So it looks like we're able to execute user operations. Now, just to make sure that this is all working properly, what I should do at this point is just make sure that somebody else can't sign this message and have it work, right? Signer 0 signed this message, and we've proved that Signer 0 signed that message by recovering the address on chain. If Signer 1 signed this message, this should not work, right? Somebody else signing the message should not work. Otherwise, our validation is broken on chain, right? So let's go ahead and execute this. And it looks like it says AA24 signature error, which is exactly what we were expecting. Looks like it's saying no. The validation came back from the smart account saying that this is an invalid signature because somebody else signed the message. Even though it's the same message, it's a different signer, so therefore this is not valid. Something I want you to think about now at this point in the video is why don't we have to do this sort of stuff, this validation, when you're doing an externally owned account, right? Why does this seem like so novel here? And the reason why is because when we do signatures on an externally owned account, we do sign them on the front end or in a script or somewhere off chain. But on chain, what's actually happening is the node itself is doing the verification, and it always does this elliptic curve, the SECP 256K1 algorithm. But what we've done here is we've done account abstraction to abstract that into the smart contract. So now the smart contract can actually choose what kind of verification it wants to do on chain. So now we have the programmatic access to be able to change what kind of validation we want to do. That's what we really gained here by moving that verification on chain. Really cool. Awesome. So what I'm going to do here is I'm just going to delete this SIG file because we no longer need it. And I'm going to move this back to Signer 0. Okay. So there is one part here that is not good enough, right? And the part here that's not good enough for what we're trying to do is the fact that we sign this message we. That does not make sense, right? Because if we're signing a message we, well, what's the problem here, right? We know that the person who signed this message we is the owner of the account. So, and we verified that on chain. So should that be enough to validate the user op? And the answer is no, right? Because once the person, like say if you're Signer 0, right? Once you sign this message and you send it to a blockchain, all of that data is perfectly visible. It's public. So if anyone wants to go look up what your signature looks like against the message we, they now can go get that signature. And they could pretend to be you. They could essentially be you for the message we, because that's already public information. In order for public key cryptography to work in the way that it needs to, we need to make every message unique and context specific, right? So when we are doing something like we're executing a user op against a smart contract, we need to sign something that proves to us that that is the intention of the user with the private key, right? The person who is signing this message, that it is this specific user operation on this entry point on this chain that is trying to do this, right? So that's really important to make sure that is very specific. That's why you have things like the nonce, right? Where we have the replay protection, all of that stuff. We need to sign this user op specifically to make sure that this cannot be replayed, right? Like the we message could be, because somebody could just grab that signature and then pretend to be you in the future. So what we need to do here is, instead of doing the catch-ack of we need to sign the message hash of the user op itself. Now, fortunately, this is actually passed to us as the second argument here that I took out earlier. It's called the user op hash. And the user op hash, we can just plug in here to the each sign message hash and then go ahead and recover the address from that. Super, super simple. Let's take a look at where that user op hash is actually being sent in, just to kind of see this from the entry point. So if I go to the entry point and I say I account, somewhere we're calling this validate user op right here, and we're passing in the op and the user op hash. Let's see where this user op hash is generated. So there's this method get user op hash, which let's go to here. Here you can see get user op hash is going to be the catch-ack hash of the user op hash, this specific entry point, right? And then also the chain ID, right? So this stuff won't be able to be replayed on a different entry point or a different chain ID. We need to make sure that the user op hash is that specific. Finally, it's going to do this hash on the user op, which is actually something that is a method inside of the user operation here. So we can go look it up right here. Here's the hash. It is the catch-ack hash of the packed values of the user op here. So it's going to be all these values packed in with ABI encode, and it's going to be the catch-ack hash of all of that. So that is what we're getting, is the user op hash. In order to get that on the front end, fortunately, this method right here, get user op hash, you'll notice is a public method. It's a public view. We can go look it up, right? So we don't have to do all this encoding on the front end and do it exactly the same way as it's being done in the smart contract. We can actually just get this user op hash on the front end, which is super, super nice. So let's go ahead and do that. So one thing that should be noted here is that when you are passing, so let's go ahead and just get the user op hash, and then I'll explain what I was going to explain, which is entry point dot get user op hash is the name of the method. We're going to pass in the user op. Now, one thing that's not used to derive the user op hash is the signature, right? That wouldn't make sense, right? Because we're signing the user op hash. So I'm just going to pass in 0x for the signature. We're going to get back the user op hash, and then from there we're going to say user op dot signature is equal to all of this, but instead of doing the catch-ack hash of we're going to do the user op hash here. And that is going to be our signature for the user op, and then we'll pass that through. Now we should be signing the user op itself, so we can't have a replay attack like we would if we were doing something like signing the message right? This is going to be a specific user op that has a specific nonce that is managed by the entry point, has a specific chain ID as we saw inside of the entry point. It's even specific to the entry point smart contract itself, right? And it has all these other parameters like the paymaster and data, all this stuff. The user is actually signing saying, here is my intention. I intend to run this user operation, not something else, right? That's why signing is not okay here. Awesome. So let's go ahead and see if we can execute this. In order to do that, I am going to need to deploy everything, unfortunately, right? Because this account is something that is created by the account factory, and the account factory was deployed right in the beginning of this video. So what I'm going to do is I'm just going to restart a blockchain. What should happen here is that when we go to redeploy these all these contracts, they should be the same address, right? Because we're starting from that same mnemonic. So hopefully this won't be too much work here. We'll just say deploy. And then when we come over to execute, these should be the same addresses, right? The factory, the entry point, and the PM, they're the same addresses as they are down here. Great. Awesome. So then what we're going to do from there is we are going to just go ahead and set the init code. And then we are going to deposit to the paymaster, and we have our signature set up. So hopefully everything should just be working like it was before with the message but now with the actual signature of the user op itself. So let's go ahead and run execute. Looks like it worked. And we want to test that we can do this a couple times. So we'll do that. We'll get rid of this, and then we'll go ahead and execute it maybe 3 times and then check our count. So let's go ahead and check our count. Let me just make sure that that sender address is the same, right? We'll bring it on over. A16, I think that's what it is. Yep. All right, so we'll go ahead and test that. All right, it's 3, awesome. And if we ran it again, it would be 4. And our last test to make sure that all of this worked is that if we go ahead and take that signer 1 and try to sign this on them, right? We try to sign the user op hash as signer 1, then this would not work here, right? So let's go ahead and try that, execute. And we can see that we're getting a signature error. So what we've done here is we've made it so that we are signing I'm going to set this back to signer 0. We are signing this on the front end inside of my script here. We're signing the user op hash and then sending that over to the back end and verifying that inside of our smart contract that the person who signed that user op hash is the owner of the smart account. So you can imagine doing all kinds of other types of verification. Like if you wanted to do something where you wanted to do like a multi-sig where you had multiple owners and they were doing, they each had to sign off like this is a valid user operation. Or if you wanted to do a different type of cryptography other than the SCCP 256K1 curve, you could do all of that stuff here. This is what account abstraction opens up for us, is this ability to be able to do this new stuff. And with the advent of the modular smart contract account, which is coming out soon, we are able to create new modules where we can install different types of cryptography that are really important for things like passkeys, where we can sign other types of messages and being able to verify those on chain so we can create new user experiences for our users. That is the name of the game for the account abstraction, creating flexibility to create great user experiences for our Web3 users. Awesome. So that is everything that we wanted to do in this step. In the next step, we're going to wrap it all up together. We're going to deploy this to a test net, which is going to involve us having to reach out to a couple different Alchemy APIs. So that's going to be really nice because we actually get to see some of the things that we would do when we were using this in a production-like environment. We're going to have to reach out to some APIs to be able to get good gas estimates. And we're also going to have to reach out to call out to a bundler, which is the bundler is actually going to put our user op on chain. Great. So I'll see you in the next video when we put all this stuff out on the testnet.